So Servo is the parallel browser engine. I kind of like more the browser engine for the 21st century, and you will understand why later. But the official name is the parallel browser engine, which is designed for both applications and embedded use. This is the unofficial official logo, and I'm not joking. The people in this project are really welcoming and funny. So I'm going to start by demoing, because I really hate when people go and be like, I'm going to talk about this project, and they spend 14 minutes talking about things and improvements, and you're like, I don't even know what you're talking me about, so please show me something. I'm going to show you something. I can't. I haven't even had a coffee yet, so imagine. So, okay, let's... Do we have internet? Supposedly, yeah. Okay, let's look up Wikipedia and hope it doesn't crash. Okay, this is Servo. This is just a shell. This is Servo, and we can scroll. This was just started 2 years ago. So for a browser that was started kind of like 2 years ago and can render all this whole thing is pretty good, I would say. Something a bit more complex. This images, tables, things. This is cool. Oops. That's what you get when a browser is new and it's not totally finished. So right now, the browser can pass the ACID 1 test. If you heard about that, you know what I mean. It's the kind of like ACID thingy. We're working on ACID 2, and Flex and Grid. Nothing of that is implemented yet. But we will talk about the future. So this is Servo. It's like this little window that just does this thing, and you press ESC to quit. Sometimes you get errors when you leave. That's fine. It's all under development. I actually am running a version I compile myself because I like the risk and danger. So yeah, that has been Servo. And now that you've seen what I'm going to talk to you about, you will be asking, like, but why are you doing this thing? You have this full-blown browser, which is called Firefox. You also have Chrome. You have like so many engines. Why would you bother creating a new one? So let's go back in time. This is the first website ever. This was Tim Berners-Lee creation because he wanted to share data and documents with more than data. He was trying to share documents with people. So he wrote this thing. He actually didn't go and program the server. He went and proposed like a server and the client, like academics do. They write a paper and they propose something, and then they might get approval and get the thing running. So eventually this happened. This was the first website. It's like really plain, boring, simple, just like links and text. This is actually the computer where the thing was running. Like this is Tim's computer, and the browser was running there. Do you want me to change? Yeah, we're changing microphones. You can look at Tim's computer in the meantime. Hi. Yeah, cool. I can wave with 2 hands now. Yeah. Yay. So yeah, so this was Tim Berners-Lee computer at CERN. And actually, if you zoom in the picture, this says, this machine is a server, please do not power down. Because the server, this was the internet back then. If you turn this thing off, the internet would go down. So obviously, he needed to make sure that no one did that. So the browser, the World Wide Web project, and the server for the World Wide Web project were all running on this thing. And it was just like a 1 CPU. I don't know if you heard about Motorola chipset. This is a 68 something processor. I think maybe 25 megahertz, just 1 core, no graphics card or anything. This is just like a desktop computer back in the days in 1989. But things happen in the meantime. We had HTML 2, 3, 4, 5. We had Ajax. Phones happen. People want to roam around with their phones and run apps and that kind of thing. So new needs have arisen since we have like those static documents and things. Users have expectations. They want to be able to run an app. And they want to run the app without the website or whatever the thing is consuming the whole battery, as Bruce pretty clearly explained. And also developers, which is not only about users, someone has to develop the apps. Developers want to be able to embed part of the browser engines on their apps. Game programmers kind of like to use HTML5 engines to render text because it's easier than writing your whole rendering text engine in C or whatever. And also something that developers would really like is not have to worry about memory issues with C++. So there is these three new things that you need. And the problem is that most of the modern browsers that we can access or we can use, they were designed before the year 2000 and also for desktop computers, and they are written in C++. There are other modern browsers, but they are research projects and they are hidden behind paywalls, so it's like virtually invisible. So Chrome, Firefox, all the other browsers, they are old, so they are not modern actually. They are kind of like from the last century. So some people at Mozilla, I'm not attributing myself with the credit, some people at Mozilla saw the need for developing a browser that supported these new types of applications and devices, like browsers that you can embed on places, browsers that you can use to use all the hardware in a machine. Like new machines have multiple cores, lots of GPU processing power, and normally browsers are not using any of that. They might use a core and maybe some of the graphics acceleration, but that's it. And also we need to make sure that the browsers are secure and modular, and I will go more into that later. So Servo is an answer to all these needs. So as you do in computing, you don't do the whole big thing just one at a time, you divide and conquer. So what we're doing here is going through the problems and fixing one problem each time. So I'm going to talk to you about three problems today. The first one is the foundation, which is solid foundations that we need with Rust. Then we're going to talk about how we're maximizing the usage of hardware using parallelization. And also, we are going to look at how Servo is embeddable by design compared to modern browsers. So problem one, building a solid foundation. You have to think about what the users want, but how much does it cost in terms of programming? That means like people programming. This is what happens when you write your own slides. So first, people want high interactivity and something that is as interactive as normal native apps. But high interactivity requires multithreading, and multithreading is really expensive to do with C++. So the need number one is expensive already. They also would like to be able to trust the browser with their data. Although after Matthias' talk is like interesting. But yeah, suppose the browser crashes really badly, then all your data might be exposed. That's not acceptable as a browser maker. So writing safe code is hard as well, especially in C++. So that's another need which is really costly. And browsers are millions of lines of C and C++. And basically, like even if you look at the percentage of bugs that we have in Gecko, 50% of the bugs, which are like the super critical must fix, like 0-day bugs that we need to fix, are a consequence of using C++. Even if the programmers are like super experienced programmers that have been programming on Firefox since before it was called Firefox. So C++ is a liability. So the basic thing that you have to take, the takeaway from here is like, if you have to write a new thing today, don't write that in C++. Write in Rust or something else, but C++ is dangerous on the long time. So the way that Servo fixes this is by using Rust, which is a new language, which is also it has also been developed in Mozilla Research. And it's memory safe by design, which means for people that have done C++, that all these problems that we have normally with C++, with memory and allocating memory and cleaning memory and dealing with memory, all that is gone. So dangling pointers, data races, integral flows, buffer overflows, those are like checks that you get by compiling. And like when you're compiling, the compiler will be like, hey, this is going to crash. You can't compile this. Buffer overflows is like runtime checks. So you have lots of checks that the language gives you for free. This is the common errors that make a browser crash and things being stolen. So the language is just preventing you from producing any of this defective code. So if you don't have to worry about memory locations, you can focus on actually writing the engine, which is really, really exciting. And the other cool thing is that parallelism is very easy with Rust because it does things like making it very easy to partition the vector. So you have a data array and you want to distribute the work across multiple threads, running multiple cores. The language will go like, oh yeah, let's go and do this thing. And it would just like do the partition really easily. And you don't have to do it yourself. So you can trust the compilers to do this thing for you. Also, you don't share data across threads. They have a thing called ownership, so only one thread can access an object at a time. That's very low, like high-level explanation. The good thing is that way you cannot create data races because if you want to touch something, it has to be given to you. There are similar things with Swift and Objective-C, but the cool thing is that this is platform independent. It's not just for Mac computers. And also concurrency is also easy to accomplish with this kind of like message passing and ownership models. So it's very easy to write parallel code with Rust. And all the experiences I've talked to, like from programmers implementing things with Servo, they are like, we can go so fast by using Rust. We don't need to worry about things which are like so low level. We can just like focus on like higher level stuff. So that's really cool. And also the other cool is that it aims to be as fast or faster than C++. And also safer, of course. So preliminary tests show that just by running the same code with the like similarly equivalent code in Rust, is like it could be like 40% faster than C without even trying to do anything optimal or anything. So it's really promising because we also have the guarantees that this memory is safe and all that kind of thing. And what I mean faster is like literally faster, but also developer hours. Like you don't have to spend time debugging, which is great. So less time debugging, more production. And the other interesting aspect here is that Rust is interoperable with C. So that means that, say, 2 years ago, someone had Rust and said, like, what if we build a browser with this? And you can be like, yeah, let's do this thing. Because you can use parts of other browsers. So you can take, for example, the SpiderMonkey JavaScript engine, which is the one in Firefox, and using the C interface, you can use that in Servo, which is what we're using right now. So in the future, we'll have time to write the whole new JavaScript engine with Rust. We can just replace the SpiderMonkey engine with the Rust engine, whatever the name is. So it's cool because we have parts of the browser which already existed, and we just took them and inserted into this Servo browser. And the other interesting thing about Rust is that it's got a package manager. So if you've done any C++ code and you try to compile a library with your code and you have dependent, no, it's not going to happen. It's just impossible. Like I was talking to my friend, she likes to program games, and I was like, oh yeah, I did something with SDL some years ago, and I tried to look, and I was like, I don't even know how to compile this thing anymore. Like I knew at the time, but because I had installed the SDL dev package in Linux back in the time, but nowadays maybe I try to install the thing with apt-get, and then the package has been renamed. I need 3 more dependencies from the stdc lib from Linux. I don't know, it might not work anymore. So it's great that this new Rust language has the notion of package manager, because you can also have versioning and the kind of things that people take for granted when they are like web developers. You don't know how fortunate you are. So Rust is really, really interesting. And it feels definitely like a 21st century language. So we have a solid foundation now. We have a language we can trust, and it's modular and la la la. So next problem, maximizing usage of hardware. But why would we want to do this maximizing thing? I think it's important to understand what kind of problem we want to make faster, because you can't just say, oh yeah, it has to run faster because it's got 3,000 cores. Like, it's not going to work like that. You need to understand what you're trying to optimize. So normally, people assume that people know how this browser thing works, but I don't think it's the case. So I figured out, maybe let's look at this and understand. So how do we go from HTML as a website thing, abstract concept, to a render thing? The browser parses the HTML and builds a DOM tree. A DOM tree is like this, like trees, but upside down, which doesn't make any sense. But yeah. So style calculation. the browser goes and looks at DOM tree, and we're going to compute what they actually call the get computed values. At this point, we don't care about the size of the viewport or anything. We just look at the like the built-in browser style sheets and the style sheets for the document, and we say like, oh, pixels or density or whatever. So it's like just values that don't depend on the size of the viewport, and we do this thing from up to the bottom, and then we go from bottom up for the next step, which is the flow construction, which is when we build the flow tree, which didn't make any sense to me, with fragments and flows, which doesn't make any sense, but I'll explain to you. The fragment is the leaves of the tree, and the flows is like the containers, like things that are not the end of the tree. So for example, a div would be a flow, and a fragment would be a text node without any container or anything. So the first step went down and the other one went up, and then we go up again because we go and look at the width of elements. That's the minimum the element wants, but doesn't mean that it's the minimum it will get. But suppose that this is an element that says I want to be 20% or 20 pixels minimum. So that's it. And then we go from the bottom down, because for finding the actual size, you need to know the size of your parent. So see, we're going through up and down the tree many times. And then for finding the block size, you need to find the size of the children. So you need to go before the bottom up again. And then finally, this is the last step. Building the display list is like going from top to bottom again and looking at all the sizes that we determine. I mean, there are other things that we are doing, but this is the basics for layout. We look at all the things that we learn going up and down tree, and then we are like, okay, this is the positions of the things, this is the blocks, and this is where things are. And we have a display list. And that doesn't render anything. But the important thing is that this has normally been super parallel. Like you just would go and do all these processes of going up and down, and it would have to be one after the other. But if you have multi-cores, why don't you just do this thing in parallel? And well, you don't do that because it's very hard to do that with C++. But it's very important that we do that in platforms which are mobile, because the cores are slower, but there are many cores. So if we can split this process in many calculations, that means that we can get faster calculations. This is an interesting data. Like 4 cores that work at lower frequency can deliver as much work as just 1 core running at the fastest frequency, but will save 60% of the memory use. If you're running things on battery, this is really relevant to you. So it's important for mobile browsers, but it's also important for all platforms, like desktop platforms, because that means that we can do more complicated pages, because parsing is going to be faster, parsing and layouting. So the way they do this is with a work stealing algorithm. They go on through, look at all the trees and the things they have to do, and they split that in a number of works, and they give some work to threads. But the important thing here is, instead of like the traditional parallelism way, is that you have threads and you give works to the threads and then wait for them to complete. These threads can still work from other queues. If one of the threads was assigned to do work on a branch of the tree, and maybe the branch of the tree is set to display none, it's like, okay, I'm done. I don't have anything else to do. So you can go and still work from other trees, which is really interesting. I'm imagining like threads stealing work from other threads and being like, I got that. Maybe they're like, it's like Pikachu's, but for threads. So the other cool thing is that because you have all these threads running, you can do all the traversals of the tree in parallel. So you don't need to wait for every step to finish. You can do many at the same time. The only thing is that for preventing data races, sometimes we're calculating some things twice, because you don't want to share code between threads. So you calculate them maybe one time, and then you just find out that you need to recalculate because something has changed. But at least you could get going. So sometimes parallelism is not perfect, but on the long term it's better. So there are more optimizations that you can do. This is a gentle introduction. I don't want to get too much because you will just fall asleep. So one of the things you can do is try to minimize calculations where possible. So we set damage flags on flows and fragments, which is those bits of the tree that I mentioned. But suppose it's just on elements. And then we know that each property can cause different types of damage. So for example, a color change won't affect position, won't affect size. So if you change the color, you say like, okay, this damage is not very substantial. I don't need to rerun the whole thing. I just need to change this local value. So it's the kind of things that we're trying to look at. Like, okay, once you parallelize things, what else can you optimize? So as I say, we just look at how the layout is built, but not how it's rendered. And there used to be another render before, but like about a year ago, not even a year ago, the 22 of September of 2015, the first commit for this one was created. And this one is a purely OpenGL-based renderer, which means that painting is super fast. And because like even like the Raspberry Pi 5, like the 50, no, sorry, the Raspberry Zero has like a super fast OpenGL render. Like GPUs are fast and there are plenty nowadays. So it makes sense to go and render using OpenGL instead of having this hybrid between CPU and GPU that we use in normal browsers. So why would we do this thing? Why not taking a ski, which is the Chrome one, or Direct2D or something like that? And the reason for this is because they are general purpose renderers, which means that they are ready to do any kind of drawing, but they are not very fast at any kind of drawing. So they are also designed for CPUs because that's where the browsers came from, and they don't know how to do GPUs properly. So what Webrender does is it takes CSS and it will do CSS, like it will just eat CSS for breakfast. And then developers can just do layout instead of worrying about like, oh, I need to do this thing because this property is slow with CSS, la la la. No, you just do CSS and you don't worry about whatever the browser is doing under the hood because that's not your problem. You just want to do your website. So in a nutshell, again, like I don't want to go super. It will take a display list, which is what the previous layout step produced, and draws into an OpenGL context. So you need some support for OpenGL and but the basic support that we need is basically the equivalent of an average phone. So it should be kind of okay. If there is support for better things, we will use them. But that means that it, it doesn't require to have like the best thing to work. Also, it works in retain mode, which I'll explain. So that opens the door to main optimizations. And it's basically like a graphics game engine. Very low level, but it's also very fast. The problem is that it's also very directed. It just works for one use case, which is drawing CSS. So roughly, we take the display list. This is more or less what a display list might look like. I don't know if it's big enough. It's like a list of things to draw on the particular specific place in the page, and then the sizes. And one of the engineers was explaining that you can pretty much represent everything on a page with 6 types of kind of like primitive, like text, solid color, box shadow, because everything ends up being rectangular somehow. So that's pretty cool. So you process this thing, and then you prepare the resources. So glyphs, which is text, you render them on the CPU for now, because we want to move this to the GPU as well. And then you eventually generate blocks, like textures with text, like basically, like literally texture rendered images. And you just move the images to the graphics card. Graphics programmers tend to like to say uploaded as textures, and I just copied that. But that doesn't mean that we're uploading anything to the internet. We're just like moving that to the graphics card. Then we also upload the images to the graphics card as texture. This was very easy. No processing required, probably. And then for paths and shadows, we use special shaders. If you don't any WebGL, this might sound familiar to you. The cool thing is that these shaders are handwritten, so we can optimize things if we need to. And actually, like adding support for new elements means literally writing shaders, which is like really funny. And the cool thing about the retain mode is that all these resources that we prepare are retained from a frame to frame. So unless you change the image or that the text changes or whatever, this is super fast because you don't need to regenerate and upload all these things to the graphics card, which like uploading things kind of like depends on the bandwidth, and that can be really slow. So once the things are in the graphics card and you just move things around, this is super fast. And this is great because that enables you to forget about the usual, oh, then just left, then just stop, because it's slow. No, it's like nothing's slow anymore. And then you just draw. So goodbye to Transformset, goodbye, because you don't need to have a new layer. Everything is in layers on things. So everything is in the graphics card. You don't need to move things to the graphics card with Transformset. That doesn't mean anything to people. You also can use top and left instead of transform, translate, and which is very strange for people. And also say goodbye to painting as the bottleneck, because painting is just like super fast now. It's gone. It's like problem solved. And then you can say hello to hundreds of frames per second. using the GPU effectively, so you don't feel bad about using the battery badly because you're doing things in the core that you could be using on the GPU. We don't use energy stupidly. And then the other interesting thing is that maybe you could use Webrender in your own app if you just know how to represent things with CSS, because Webrender is another module that we can take out of Servo. So it's interesting because it opens the web to opens the door to sharing these features with more things than just the web. So Webrender demo. Oops, you're seeing the secrets. So this one is rendering using top and left to change positions of divs. I will show you in Firefox first, so you see how painful it is for normal browsers. It took some time. And then the same one with Servo. You can see the difference. I'm also going to say that these demos were written by my intern, Sam, who will watch this. Thank you, Sam. He was really talented and great this summer. So that's great. We have a thing that is very safe, very soundly, like good foundation. We have fast rendering. So where should we use this thing? So we can use this as a browser, or we can use that in other places. And Servo has been designed to be embedded. So you have a game, you could embed it as your, like HTML rendering UI thingy. And the other cool thing is that you can take as many parts as you like to take. You don't need to take the whole browser. You can take just a few components like Webrender, or maybe the whole browser. And that's because it's modular, because it's using the cargo package manager. So instead of being this super mega repo, I think Robert might have some memories of Mozilla Central. Instead of being this mega repo that takes hours to download, this is just like few repos that download other repos like npm. So things are decoupled. It consumes packages from the ecosystem. Instead of being, here's the Firefox repository where things go to die, this is like where this is the Rust repository where you have things and you consume things from the other ecosystem. And you can also contribute packages to the ecosystem, which I'll show you later. The cool thing is that this makes it very easy for people to start contributing to Servo, because they just need to look at one package, not at the whole thing and navigate the whole directory. And it's also easy to replace parts. Like, as I say, the Webrender is new. It's not even a year old. And it wasn't, I think it was enabled in February, but we just had to replace one renderer. So that's pretty cool. And if you ever try to embed a browser in your application, you will understand the pain here. The API changes a lot, and it's not. They were not designed to be embedded, but Servo is, because it's got defined and tested API, which means that you don't have the problems that Node.js people have when V8 is updated, where they have to like keep up to date with the changes and everything. With Servo, everything is very clear and defined, so it should be easy. Exposes as C interface, so that means that you can consume C, but you can also be used as C. So I know that TV, like I won't say names, but I know that TV builders or manufacturers are using Servo to display the menus and things like that. But you could also use that to write your video game UI interface and la la la. And maybe there are new applications that we don't know about, but because you can embed it easily, there might be new things happening. Maybe Internet of Things stuff, I don't know. We'll see. So the future, when I started looking about Servo, I was like, when can I use this as my main browser? This is amazing. And the answer is never, because it's just an engine. So, I mean, a browser, we always expect that it's just the thingy that renders, but the engine is just the engine. The browser is more than just the engine. You have the thing that keeps the bookmarks, the history, like the tabs, the shells, the Chrome around, everything. So I think I would say never is a good answer. But actually today, you can also use that via Oxidation. I like oxymorons. So Oxidation, it's a project to integrate Rust code into Firefox and Gecko. So we don't need to wait until Servo is totally complete. So we don't need to have the shell and all that. We can start using things today. So actually, if you have downloaded Firefox since August, you've been using Rust code already, but you didn't know that because it's so perfect you couldn't even notice. We've used that for the MP4 metadata parser, which is a bit that takes videos and parses the metadata. You would think that this is something so simple and ridiculous, but it's actually a big source of bugs. Because people try to exploit it by sending you videos which are badly formatted, so they can crash your browser and steal your data. So we ran an experiment with the browser, with the beta and nightly versions, where the C code was running parallel with Rust code, and we got like telemetry data to make sure that there were no bugs or errors, and also that the performance of the Rust code was as fast as the C++ code, and it turns out the failure rate was 0. So we turned it on in August, and it's running on all the platforms. I think macOS 64, 32, 5. I think the only one that is not running on yet is Android. But that's really impressive. And also the new one that we might be enabling as well is the URL parser, which you would be surprised, but this is also a huge source of bugs because there's a lot of string handling on URL parsing, and URLs can be really big. But there are also lots of edge cases, and in general, if you can make URL parsing, which is I think browsers do all the time, really robust, you're going to like protect yourself. And also there are so many libraries in JavaScript to parse URLs. If you could just share that with the ecosystem, which is what we are doing, that's going to be great because you don't need to rewrite yet another implementation of URL parsing. There is another project for calculating styles, and I think selector matching for CSS. If we can do this thing in parallel, which is possible, you're also speeding up your page. More things which are just for, which are calculated in parallel, like WebM processing and things like that. So this is all great because you, for example, for videos, you don't need, normally you can be in a situation where you can decode several frames in parallel instead of waiting for one after the other. So that's really cool. So there might be more maybe in the future, we'll see. And I mentioned a little bit on the abstract about the community in Servo and why it's so great. It's funny because we had a meeting with I just invited 2 persons in the meeting from the Servo team, and literally 13 people show up to the meeting because they were so excited to work with us. And I was like, this is the first time engineers come to us, like out of their own volition. So they're really nice people, and their standards are really high because in the Rust community they also have like really high standards. Like the code of conduct is upfront. There is no discussion. It's like, no, we have to be decent human beings and respect each other. Also, it's interesting, the code for Rust and the Servo code is also on GitHub instead of being in our own private repository because developers are in GitHub. Let's face that. So you don't want to put barriers of entry. You want to make it easier for people to contribute to your project. Also important, labeling bugs by difficulties. So newcomers know what to pick. Because sometimes it's like, yeah, come and contribute and fix bugs. And you're like, but where should I start? And there isn't even a list of good things to start with. And something really important, having good bug descriptions that tell you what to fix, where to fix, here's the documentation, here's the spec, look at this. That's so great. And important as well is that when you file a bug, which is what I do often, there is someone that will look at the thing and say, oh yeah, I could reproduce this, thank you. Instead of, like sometimes you file bugs in some other projects, some people are like, tumbleweed, and nothing happens for years, and you're so frustrated you stop eventually contributing to the project. So sometimes it happens that people try the bug and fix that in hours, so that's really, really exciting if you're trying to get things done. Also, for things that don't require humans, there are lots of bots. Like if you don't need a human to tell you that you have some stray white space or a missing a semicolon or whatever. There is a bot that will tell you, so there are no hard feelings. It's just a bot. And the bots have the doggy everywhere, so it's all really funny. Also interesting is there is this weekly blog post where they will go, oh, this week we did this thing, this is what we fixed. So you can have a high level overview, but they also thank new people and recognize the contributions of people instead of saying like, we, as a global we have done this. And it's like, but who did this thing? So they are attributing authorship to people, which is really encouraging. And in general, there are really nice people there. And so this is a screenshot of the usual blog. This is last week or the previous week. So you can see that they are like thinking, explaining things, la 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 la. This is an example of a bug report, which is like really explained. I think this is just adding a property to the navigator object, but there is this whole explanation, and there's a whole explanation that goes under. And so they use these labels to categorize things. So if you want to pick an easy bug, you just go for easy. So this is really useful because then, for example, I wanted to file a bug and I didn't know how to do it, so I just looked at existing bugs and I just copied the format. Like, it's really good examples. So if you're intrigued, which I hope you are, we have nightly builds. Like, up until 2 months ago, you had to compile everything, but now we have nightly builds and you don't need to spend 3 hours. In my laptop, which is really underpowered, it could take 3 hours to compile. So you can just download it and play with that. I think someone's preparing Homebrew packages if you run Mac, so that's great. There's probably some apt-get repository somewhere, so you can download it. And if you want to play with that, just an easy way is just go and watch if it works in your favorite website, and if it doesn't, just file a bug, and that would be great. Or if you really need for some hotness in your legs, just compile from source. This is amazing as well. This is one of the few projects which requires compiling that I could get to compile just by following the instructions on the README instead of having to chase some developer to explain me why this particular step wouldn't work. Really good instructions. So recap, tackling one problem at a time, these 3 problems, getting rid of C++, using hardware better, and also making embedding possible, and community building efforts pay off because it sets the tone. If you have a welcoming environment, it's nicer to work with this kind of people instead of feeling like, oh, they are judging me. And this is the best slide. It's like, Froch is right. Such pros, many parallel. And I have a final gift for you. It's our funny demo that we built. This was our benchmark. So the first one in Firefox, it just counts the number of doggies that you can get. Eventually it gets like, oh, I can't, I'm slow, and it starts to die. But the same one in Servo is really fast. The problem is that the number is missing because something else has been broken. But but we've had so much fun, and yeah, seriously, like some of the demos are really cool. Let me just go and show you. Also, this is the project that Sam has been working on. The network works, doesn't work. It does work. Maybe I should use local. Anyway, this is the experiments that we've been working on, and this is my contribution to the experiments. Just testing, because we needed to know if the filters would work. So last week when we did this thing, it like all the lower experiments wouldn't work. Like no transformation would work because it couldn't do the iframes. But they did that. They fixed that with all the issues. Now it should work nicely in Servo. Maybe not. This is because I compiled it yesterday and I didn't try that. Anyway, it's cool, it's changing, it breaks, and then it gets fixed. So thanks, and I hope you try and enjoy it with me.
Thanks. So, we still have a few minutes before we are breaking for our dessert break. Is there any questions for Sol? There's one from Matthias here.
Yeah, I was interested in the Webrender thing. Why has no one come up with this before? And can other browsers do something similar and implement it as well?
Could they do something similar?
Yeah, to speed up the rendering by such great amounts.
I guess they could. If they haven't done it, it's because they are very tied together. So separating pipelines. I was actually reading, when I was documenting for this, I was reading the story of the person that implemented hardware acceleration in Android, and like it was like they have to manually move things to the new layer, and it's like the CSS engine is very coupled with all things. So I guess this is a consequence of the inheritance of. I guess it could be possible, but the issue is that when you want to do that in a fast way, you need to use threads and C++, la 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 la. But I could ask for more clarification if you're interested.
All right, let's give Sol a hand.